Good morning, everyone, once again, and welcome to today's webinar. And today's webinar is on multi-GPU programming in NCCL and NVSHMEM, which is shared memory. We are glad to welcome you and talk about high-performance communication software for GPU supercomputers. Today's speaker is Jeff Hammond, a distinguished engineer at NVIDIA in the data center software organization focused on GPU communications. He has extensive experience with the design and use of parallel programming models in scientific applications. Jeff's most notable achievements include the MPI 5 application binary interface standard, the development of the MPI 3 one-sided communication software ecosystem, and contributions to the NWChem quantum chemistry project. He received a PhD in chemistry from the University of Chicago in 2009. So please welcome Jeff to our webinar. Thank you once again, Jeff, for joining us. So just some notes. I would like to inform you that you can and should interact during the presentation. To do so, you can use the chat to share your questions. During the presentation, there are no discussion moments, but at the end of the webinar, we'll provide some minutes to discuss all the questions and interact directly with you. I'll be monitoring chat activity regularly, ensuring that all questions are dealt with and by the speaker at the right time. So now we move to the presentation. Jeff, the screen is yours. Thank you.
All right. Cool. All right. Thanks everybody for being here. So, my interactions with DEIC, I don't know if the right pronunciation, but this is primarily an HPC audience, and so this talk is really designed to connect classic HPC communications to GPU communication software. As noted, I've been doing MPI for a really long time. I like it a lot, and Nickel is very much, sort of descended from MPI and NVSHMEM, likewise from SHMEM and OpenSHMEM. And so I'm going to talk about that relationship, and then what's in these things, and then show you some examples that of what's interesting, what you can do with GPU programming, that's in some ways pretty different from what we can do today with MPI. So I'm gonna start with a couple of numbers that I like, that I think programmers should think about numbers when they design applications, and the numbers have changed over the years. I've been doing this for 20 years, and the numbers keep getting bigger, in the right way. And so think about 40 million of something and 2 billion of something. So these are both big, right? These are big numbers. Whatever it is, if it's a good thing, you probably like it. And so what could you do with 40 million? Well, what are they? Well, so these are math operations. So and then of course there's a time scale. And actually I think I normalized this wrong. So forget about the op per second, because it's actually per microsecond, right? So the motivation for a lot of the things that we want to do in GPU communications is that you can do 40 million HPC math ops, FP64, in 1 microsecond, and you can do 2 billion or more AI math ops in 1 microsecond. And the reason I normalized to microsecond is because microsecond is about the time scale of data movement. So if you do a GPU kernel launch, it's going to be 3 microseconds. If you do a MPI ping pong latency, best case scenario, it's about 1 microsecond. And so you think about what could you do in 1 microsecond with the compute? You could do a whole lot of math. And so if you're wasting microseconds, you are wasting a lot of math. And so that's the idea here, is let's not waste microseconds. Let's be as efficient as possible with our communication, regardless of where it is. And in some cases, what we're going to talk about is that moving the communication to the GPU and moving away from traditional send-receive patterns is going to be a good thing. So just an overview. Nickel started out about a little over 10 years ago. It was originally created because I can't remember what the framework, AlexNet, ResNet. It was sort of in the good old days when life was really simple. Um, we're doing, basically an all reduce between 4 GPUs in a workstation. It was a very, very simple world. And even that was a little bit hard because of PCIe topologies. And obviously it's evolved over the years. So now Nickel supports, all the communication operations, and I'll talk a little bit about what's in that set. And then all the platforms. So it still supports, workstations full of PCIe cards, although that's not the focus. It supports the NVLink domain, which is growing from, 4 if you're on a ULISH GH200 system to 8 if you're on a DGX H100 like Gefion, Copenhagen. And then, NVL72 is being deployed in the AI world and now also in HPC sometimes. And then scaling all the way out to 100,000 GPUs with InfiniBand and Rocky. So huge amount of scale. And then obviously, as the scale of the system grows larger, communication overheads become more and more critical. So Nickel supports all of the AI communication patterns. So, you got the basic stuff, all reduce, all gather, reduce, scatter that you used a lot of places. You have send receive for doing sort of unstructured, communication and pipeline parallelism. And then increasingly, there's all patterns showing up in mixture of experts style. And if you want to know more about Nickel, there's a great GTC talk that Sylvain has been doing. So you can check that out for more details and some of the performance baselines for the collective. So I'm going to focus just on all in this talk. The Nickel ecosystem is quite large. It does have usage in HPC, but is primarily driven by the AI market with all the platform providers and then all the frameworks connecting into Nickel. One of the interesting things, folks may have heard about DeepSeek, and DeepSeek had started out using NVSHMEM in a really creative way, and that's the inspiration for some of the things in this talk. And they actually switched in DeepSeek v4 to using Nickel because we designed some new features around the expert parallel model that they were able to take advantage of. So the host API, and obviously this is not a full tutorial. There's not enough time to go through everything. So I'm just going to show some basic examples, and then you can look at obviously our documentation, our blogs, and then I have this GPU mode video that's quite long that goes through a little bit more detail. And then there's other GPU mode videos. Umad, I think, has one, and there's a couple others on Nickel that are on there. Marcus Herniak, you can check out. So we have all reduce, looks a whole lot like MPI, with one critical difference, which is it takes a CUDA stream, and that's really sort of the genesis of why Nickel isn't MPI, is that you need to be stream aware to do GPU communication. There's also send receive, and send receive happen in a group. This is an interesting pattern that's different from the way MPI works. And I think if MPI really knew what the future was going to hold 20 years from now, when they started in the 1993, they might have done something more like this, because this really captures the pattern that a lot of applications are actually using, and it's easier to implement efficiently when you group these collections of send receives with the Nickel design. And this is critical for us with handling some forward progress issues with how the GPUs work. But it is generally useful to sort of tell the network or tell the system about your whole collection of send receives. So NVSHMEM has a different pedigree. You can watch another GTC talk by Keel and Jim about sort of the full picture. But the idea of NVSHMEM was very, very different. It was not inspired by MPI. It was inspired by SHMEM. And SHMEM has this model of the symmetric heap, where you sort of say, I have an allocator. I'm going to collectively allocate memory across all my GPUs. And then these GPUs can all access one another's data directly using something that looks like memcopy, or in some cases, the equal sign. So if you're on an NVLink domain, you could do load store, and you could just say, give me a pointer and go. And I'll show that in the rest of this talk. You can also generally use put and get, which look like memcopy. And those, of course, will go over NVLink or over a network like IB. efficiently. And then, the big thing in NVSHMEM is that these communication operations were supported directly from the GPU in addition to the host, whereas Nickel has until about 2 years ago been completely host orchestrated. NVSHMEM was designed to be device orchestrated, and that was sort of this fundamental philosophical divide and why they coexisted. And what we've learned now is that it's important to bring some of these NVSHMEM features into Nickel. So that's part of this talk. So NVSHMEM has a smaller ecosystem, but it's still an important one. DeepSeek obviously picked it up and brought it to the AI community. Perplexity has done some nice work with it as well that I'll refer to later. It's supported in some of the frameworks for symmetric memory. We also dog food it in our math libraries because it allows us to write some really efficient, dense linear algebra kernels and FFTs native on the GPU. That where being able to do GPU initiated communication is significantly more efficient than what we could do coming off of the host. So the APIs, if you're familiar with SHMEM, they're basically the same thing with the NV prefix. So there's a basic host put mem that looks exactly like OpenSHMEM, and then there's the stream version, which is the one you should always use because you should always be stream aware in your communication to not block the device for no reason. And then there's the device versions, and we have 3 versions. One of them is a thread version, so every GPU thread will call put, and that may or may not be the most efficient thing because of how GPU threads access memory. So there's a block and a warp version which resemble the right way to do sort of coalesced memory access the way you do. So if you're doing a mem copy, you'd want to have all the threads in a warp working together. And so that's something that exists there. And so if you're doing bulk put operations, you want to use those like you would mem copy. And then there's a lot of other operations, atomics, collectives, etc. You can even do collectives from the GPU. You have to be careful in how you do it to not deadlock, but it's supported once you use cooperative groups. So now this is the new thing. So if you've spent any time looking at Nickel and NVSHMEM, not recently, you probably missed this. This is the part of the Nickel device API. And so these are APIs that allow you to do symmetric memory from Nickel, just like NVSHMEM. These APIs are a little bit more complicated. And part of the reason is that Nickel has communicators, just like MPI, and therefore it has to have these window objects, just like MPI, that allow you to put multiple symmetric heaps with different collections of GPUs. Whereas in NVSHMEM, you just say, here's all the GPUs, they all allocate memory together, and if that works for you, great. If that doesn't work for you, you're kind of stuck. SHMEM teams don't work as generally as MPI communicators. So if you're thinking an MPI model with where you use subcommunicators, you're really going to have to adapt to the Nickel model. It is more complicated, but so frankly is MPI. So you can get a pointer if you're on an NVLink domain. You can say, give me the pointer for this GPU. And then you can just use it like its local memory with obviously a performance difference. You can get a multi-mem pointer to use the multicast collective capability, so you can write your own multicast collectives. And then you can do GIN, which is GPU initiated networking, and that means you can generate InfiniBand, etc., straight off of the GPU. And those features were designed very carefully to match the usage models we were seeing in DeepSeek, for example, where they were using NVSHMEM, but they were actually using NVSHMEM they were actually hacking through some of the public APIs to get to some lower level features for performance, and we made those things more visible in Nickel because we were really trying to enable AI performance. So you can check this stuff out. It's going to evolve. It's one of our biggest initiatives, and we'll keep building in more and more capability. But as I noted, DeepSeek v4 has already adopted this stuff, and so we believe it's going to be quite important in the AI space in the future. So historical context. So I've talked a little bit about MPI and SHMEM already, but they really have totally different philosophical origins. MPI was this amalgam of prior art. So there were, every different supercomputer you bought in 1992 had its own messaging library. And many of them look the same, both because the patterns of communication were well understood, and because, of course, vendors wanted to be able to sell you a new machine and move you from machine A to machine B. So they would implement an API that was a lot like somebody else's. But of course, having to change your code every time you buy a new machine is really annoying. So everybody, users and vendors, wanted, for different reasons, but ultimately good ones, to be able to move back and forth between machines. And then the model is very much, isomorphic at some level to POSIX sockets. So you could say it's universally portable. There's no way you can't have a machine that somehow doesn't know how to run MPI. It's always going to work one way or the other. If that machine has a network that is a network by any modern computer standards, it's fine. Two-sided communication was really successful. It's easy to reason about. It matches a lot of physics. It combines synchronization and data movement, which is a good thing for usability and a bad thing for performance and some limits, and that's something that we'll get back to. So SHMEM was quite different. SHMEM was actually created for the Cray T3D specifically because they had some really neat hardware, absolutely state-of-the-art, revolutionary hardware, and they wanted to expose it to programmers in a reasonable way, so they created SHMEM, and SHMEM turned out to be very, very successful, and then more and more vendors started implementing it, and it got picked up. SHMEM has a very different philosophy than MPI. I know these folks well, and their attitude on communication software is it should either be fast or don't bother. Don't make a highly portable, slow version of SHMEM because they want applications to be designed for high performance networks. And there's things that you do when you have a really fancy RDMA network or SMP that you don't do if you're running over, token ring Ethernet or something. And so the design philosophy was very, very different. But over 20 years, they've kind of converged where OpenSHMEM is largely portable to all the systems, in part because there's an MPI version of it that I helped create. And then MPI has one-sided communication, and therefore should work absolutely everywhere. So you can read a little bit more about this history, but these are the two sort of ancestors of Nickel and NVSHMEM. And philosophically, Nickel doesn't have the same MPI attitude of absolute portability at any cost. It's very much it better be the fastest thing that exists. But from the standpoint of the actual semantics in the APIs, they're aligned. So two-sided communication, I think everybody has probably written send receive at some point. Whether they use it every day or not is an open question. But the thing about send receive that's interesting is you mostly know what's going on at both ends, but you don't know one critical piece of information about the other side, which is you provide an input buffer and you don't know where the data actually goes on the other side. You are going to tell it, here's some data, here it comes, here's the size of it, here's the type of it, and give it metadata so it knows which message it is in your application. But ultimately, there has to be some sort of matching going on between the sender and the receiver to make the buffers line up. And that means there's a synchronization somewhere in the pipeline. One of the many protocols for doing this looks like this. This is a rendezvous protocol where the sender will send over a message, the receiver will do something, send back metadata, and then the sender will move the data. And this is very powerful, very general. It's been very successful. But you think about what you want to do. When we go back to the very beginning of microseconds, there's a microsecond here and a microsecond there, and then you move the data. So you just wasted some time, and you might waste that time over and over again if you do a lot of send receives. In contrast, when you do a put, which is really writing to memory, the caller, the initiator, knows exactly where everything's going. So in the SHMEM model, you've got a symmetric pointer. In the RMA model of MPI, you've got an offset, but they're the same thing. You know exactly where the data is going. And so if you can imagine if this was a shared memory network, you would just do stores and be done. And this is an RDMA network, you can just hit the M key and go, and it will write to where it goes. So there is no synchronization. the synchronization happened up front. So I'll skip get. Get is exactly like put, it's just the other side pulling. But in the SHMEM model or the Windows model of MPI, you do that exchange, that rendezvous once up front with all the different GPUs or CPUs participating and saying, here's where everybody's data is. Now we're done. And so that means that when you actually get to that data step with put or get, it just goes. So you take all those microseconds that are going to happen every single time in send receive, and you turn them into a few more microseconds that happen hopefully once in your application. So why is this important? You really don't want to synchronize. That's been true for forever, but it's increasingly expensive to synchronize because our compute engines are more and more powerful, and even our networks are more powerful. The bandwidth that you can move in 1 microsecond is much more data than you used to be able in the past. So the amount of things you could be doing every time you do 1 microsecond of synchronization is much more costly, and we don't want to do that. We also think about, if you have send receives, you're not just potentially synchronizing between 2 processes. You may also be synchronizing with the GPU and the CPU, depending on who's initiating it and how things are going. You also don't want to have synchronization within a GPU. So if you imagine GPUs doing send receive with other GPUs, even if those things are independent within a GPU, you might synchronize some of the SMs. And again, you're wasting compute every time you do that. The other part of this is the way our systems are designed. Computer architects are really good at things that look like memcopy. We've got all sorts of magical hardware widgets everywhere in our data center systems for copying data from one place to another. We do not, unfortunately, have a lot of magic widgets that do message matching. There are some, they're relatively custom for HPC, and they always seem to have some sort of issues with them once we actually get them. And so it's proven to be something where if you can turn it into something that looks like memcopy, performance is better. The other part of this is just why bother synchronizing when you don't have to? So most AI and HPC communication is persistent. You think about an iterative solver, any sort of iterative method is likely going to do some setup and then do the same thing, same communication over and over again, probably with the exact same buffers, may or may not be, but usually with the same buffers, 100, 1,000, million times. And why would you want to do a step 1,000,000 times when you could do it once at the top? So this is the argument for doing one-sided communication, setting things up once and then grinding away over and over again, and then of course hopefully overlapping that with communication or computation. So one thing I often get asked about is nickel looks a lot like MPI, and it does it if you zoom out a little bit. If you zoom in, it's a little bit different, and these differences are really important. So nickel and MPI do the exact same thing in the common case. They all have send receive with 1,000 here and 1,000 there, or contiguous data, etc. But MPI lets you do some weird stuff. It allows you to receive with 1,000 and send only 500. And MPI has to figure out, oh, you're only going to get 500, so you got to know when to stop. That takes some logic. In MPI, you can use MPI data types to do some really interesting stuff, which isn't necessarily optimizable in hardware or even optimizable in software. Sometimes it's just plain hard and bad. MPI supports tag matching, which is, not just sort of communicator matching, which is really useful in some scenarios, but adds another layer of logic. There's also these things called wildcards, which all the hardware people absolutely hate because they sort of stop the presses when you think about, doing a hardware design pattern for matching things. You can match everything until you get the wildcard, and then you have to stop and basically flush or synchronize the pipeline. The other thing is that MPI, is usually thinking about 1 MPI rank per core or per NUMA or something, and doesn't necessarily match with 1 per GPU, and that's really what nickel is designed for. So we have these fundamental differences. Nickel doesn't support any of these sort of less common features that MPI does because they're all hard to implement, and generally speaking, they haven't been necessary in AI. MPI 4 finally allowed you to turn some of them off, but I've asked and no one optimizes. So this is something where you can, there are people out there who think, oh, nickel should just become MPI and we should just move back and everybody should use MPI. Well, it's a lot harder than that once you go look at some of the details. It will be very, very hard for MPI to behave exactly like nickel. Nickel's going to stick around for a good long time, and I think this is one of the reasons. Don't wait for MPI to be exactly like nickel. Go out, learn nickel. If you know MPI, you'll have a good time learning nickel. No big deal. But they're gonna coexist happily for many years in the future, and I hope that nickel gets adopted in HPC, not just AI, where people need GPU native communications that is pretty straightforward, which it is in nickel. In MPI, GPU support is a little bit complicated. All right, so now I'm going to talk about doing GPU comms and show some short examples. There's a very, very long version of this in the GPU mode video that's cited on the first page. You could check it out. It's like an hour of step-by-step for all the different versions. I'm not doing that here, but if you're interested in doing it, and then there's the code that's all on GitHub. If you want to reproduce it yourself or play around with it. So I did some experiments on a DGX H100. I did this because I have this box in Helsinki, and it's obviously got a lot of capability, and it's got an NVLink domain of 8 GPUs. So I'm going to study the NVLink part of this because that's something that I think is a lot more novel for most people. I think everybody is pretty comfortable with InfiniBand and Ethernet at this point, but NVLink is maybe something you're not used to doing, and I'm going to show how NVLink is fun. This is I'm going to use a benchmark that's existed for a long time. So I used to be at Intel. I worked with Tim Matson, and he had created some of this stuff with my now colleague Rob van der Wingart, and a bunch of us did a really big study about 10 years ago on a Cray supercomputer, and we looked at a bunch of communication operations, and we compared MPI to SHMEM and then to some other models. So I had this code laying around, and I said, okay, well, I know that this is a really good benchmark for studying MPI versus SHMEM on a Cray machine, so I'm going to use this code. And so the specific benchmark I'm going to look at is matrix transpose, because it's an all-to-all pattern, and that all-to-all pattern is sort of a simplified version of what you'd see in an FFT, a parallel sort, or expert parallelism. So it's simpler than all those, but it's got basic characteristics. And since those patterns are interesting to a bunch of different communities, I thought I would study this. You can see some of the details, and there's another YouTube video where I talk about this benchmark set in more detail with George Hager. So matrix transpose looks like this. So you have 8 GPUs, and you distribute your matrix column-wise. So each GPU gets a bunch of columns across the matrix, and then when you do the transpose, obviously you move those columns into rows. So if you follow one of these columns, you block it up into eight squares, and then each one of the squares in every column goes to a different GPU. So you think about it, 8 GPUs sending one block to every other GPU, so it's all-to-all. You can obviously write it with MPI all-to-all. You can write it with send receive. You can write it with put and get. And so that's the comparison I'm gonna use here. So again, you can find the details online, but there are 3 different versions, and then with some modifications to each one, variations to each one. So the first one is a very simple all-to-all. I just call all-to-all, move all the blocks, and then, of course, because this is a matrix transpose, once I'm done moving all the blocks, then I transpose each local block, and then I accumulate it to the output, and then I increment the input. And the incrementing the input is not important. It's not part of matrix transpose. It's actually part of validation in this algorithm, because we didn't want to get a scenario where if we transpose twice, we got the same data back, because then you can't tell if it's working in all cases when you do that. So the upper right hand algorithm is the Python pseudocode. But so we're going to do this accumulating transpose and then increment A just to keep ourselves honest. So there's a send receive version of this that's just send pairwise exchange on the blocks, which is just a variant of all, uses less memory because it does one block at a time. We've also got a version that does get. There's a put version, but I don't have the GPU implementation of put. It doesn't matter on NVLink right now. In general, you'd prefer put, but it was easier to write the get version. So it's an exercise for the reader to write it with put instead of get. But basically, you just go through the blocks, you fetch the block instead of send receiving it, do all the same math things, do a barrier, and then go on. Now, the fun version of this is you take the get version, instead of getting the block as a copy, you get the block pointer, and then you just pass the pointer directly to the transpose kernel. So this is something you can do through the magic of NVLink as a memory fabric, is you can just take a pointer to another GPU's memory and give it to a CUDA kernel, and just like CUDA will hide memory latency and maximize bandwidth through the HBM system on the local GPU, it will do the same thing across NVLink to some other GPU. And we're going to see how well this works. And this is important because the performance difference is noticeable even in this simple kernel, but it becomes increasingly noticeable as you go to more complicated patterns where fine-grained communication and overlap is really important. So just to distill down the results, so you've got at the bottom, oh shoot, I'm back. If I, hopefully, right?
Yes.
Sorry, my internet went. Thank you. Yeah. So the bottom version, the blue line is, and this is just the NVSHMEM numbers, but the nickel ones, are similar. For all send receive all to all is about the same as NVSHMEM all to all. So what we do here, the bottom is just the all to all version, and then each block is a different kernel. And I said, okay, well that's a naive way to do it that matches the CPU version perfectly, but then I can just fuse them all and fire them off as one mega kernel. I did that. It makes a teeny bit of difference with small block sizes, as one would expect. Then the next version, it gets a little bit better when you do get, so you can get, less synchronization in the get version, but you're still doing a block copy. And then the big jump happens when you remove the copy. Now, obviously, when you're going across a network, you are doing a copy. The memory systems are not connected. You can't do load store across most networks, but you can do that across NVLink. And so what you get here is, if you do the performance model breakdown on transpose, you've got part of this is network, or part of this is moving across the NVLink network at, I can't remember what it was, 3 terabytes a second aggregate, I think, and then it's like 24 terabytes a second aggregate to all the 8 GPUs memory. So it's like an order of magnitude difference, right? So you've got 2 steps that are local memory and 1 step that's NVLink. But you do this copy, you move data twice basically, because you move it into local memory and then you move it into the GPU. But if you do the direct access version with NVLink, you just move it once. It comes straight out of remote memory over NVLink into the registers and back out. So you eliminate data movement altogether, and that obviously bumps up the performance quite a bit. The other thing that's really neat is the version that uses direct access is actually easier to write and easier to read. It's the simplest thing you can imagine. All you do is grab the pointer and pretend like it's local memory. So you really can think of things as sort of one big GPU. You just have to schedule the compute kernels on the GPUs, but the memory itself is like one big memory space. Performance differences, of course, but from a programming perspective, it's really beautiful. So how does this show up in AI inference? there's the mixture of experts pattern, and I refer to my friends at Perplexity, who has this really nice blog. I recommend everybody read it if you're interested in either AI or GPU comms. And what they have here is, each GPU is doing some local AI stuff, but instead of doing a big gigantic tensor operation, there's a routing function on each GPU that then takes these various tokens and scatters them. Each GPU takes its tokens, scatters some of them to other experts, and each one of those experts run its own AI compute kernel. And then you reverse the process where you bring all that data back to the GPU that sent it and sum up all those contributions, and then go back to doing local operations. So you look at this is mostly an all-to-all. It's not necessarily structured. You're not guaranteed to send the same number of tokens to every expert. You're not guaranteed to send something to every expert. So it's kind of like an all-to-all V, which is harder to optimize. But you can see you can do this with point-to-point as well, and that's really the neat trick that was discovered by DeepSeek and then also implemented by Perplexity and others. So these things look like send receive. They're implemented with one-sided using put and notify and wait. You can read about that, but that's essentially the pattern for doing send receive. When you do one-sided version of it, it splits up the data movement and the synchronization, and it doesn't do matching. It just says, here's the data, and then tell you that the data arrived. Think of it like a mailbox. I don't know how mailboxes work in every country, but at least in the United States, when the mail person puts the mail in your mailbox, he flips the flag up, and then you can look from your front window and see, oh, the flag is up, therefore I know the mail has arrived. Same thing. You hit the signal and say, okay, the data is now in the buffer where it was supposed to be. You can go read it, and you can do that. Process becomes very efficient, very asynchronous. So here's the punchline in performance. So you see the original versions using an all-to-all kernel, first with NVSHMEM, 2 different IB versions, and then whatever Torch was doing. This is a pretty substantially amount of time. It's about 5,000 microseconds. So that's visible. Like from a human standpoint, 5 milliseconds is something that we're capable of noticing. And we're talking about inference, so this is human interactive loop computation in many cases. And then you look at what they did with dispatch and combine. So Perplexity has a different implementation than DeepSeek. DeepSeek's implementation is specialized for InfiniBand and is faster because they were optimizing in a way that doesn't work on anything other than InfiniBand. Whereas Perplexity, they also run on Amazon's EFA network, and so they weren't willing to specialize for IB. So they only benchmarked against IB here, obviously, 2 different versions with IB. But they kept the NVSHMEM API the way it was so that they could be portable to other networks. So they lose a bit of performance on that basis, but you can see here, this is, 2 orders of magnitude or so improvement over the all-to-all based version of the expert parallelism, and this makes a huge difference. I don't know if I use Perplexity every day. I don't know if others do, but if you used any of these LLM chatbots, you type in something and then it cooks for a couple seconds and then stuff comes back, and if that's 10 or 100 times faster, you notice, and that's has been a really significant achievement for a lot of these folks doing inference engines to be able to use high performance expert parallelism, and that comes out of doing better GPU communications, sometimes taking advantage of InfiniBand, sometimes taking advantage of NVLink. So I'll show some HPC applications because not everyone loves AI. There are similar use cases in GROMACS. There are NVLink use cases, which are really good. This is an InfiniBand use case. And you see here, if you know molecular dynamics is a relatively small number of atoms computing the interactions and then doing time stepping. And so you have to finish the time step you're on before you go to the next one. And therefore is a very hard latency wall that is often limited by communication. So when you want to exchange your short range interactions within your neighbors or do long range interactions with FFTs, you've got a whole bunch of communication steps that have to happen before you can move to the next step. And so you can see here, as the number of GPUs increases, the communication overheads are obviously becoming more significant. Compute scales almost linearly, communication doesn't, communication time grows, but then the performance you get from switching from MPI to NVSHMEM shows up and makes a big difference. And then this actually becomes a really, really huge difference with NVLink, but I don't have that number here. Another one you can look at is in quantum computing, and this is important to some folks. These are really big numbers because this is a scenario where there's a lot of all-to-all communication in quantum computing because you basically have all the qubits interacting with all the other qubits. You distribute your state vectors, and then you apply Hamiltonian to them, and you're going to couple that state vector to the whole rest of the system. So we don't have any massively parallel multi-node CPU implementations of this stuff because I guess nobody's inspired to write them because the performance probably won't be that good because it's all and the bisection bandwidth won't be high enough. So NVLink has enough bisection bandwidth to make this interesting, and therefore you can implement a 64 or 72 GPU version of some of these algorithms, whereas you probably couldn't or wouldn't be happy with implementing a 64 or 72 node or socket CPU version. So you can see down there at the bottom, obviously it's comparing to a really, really powerful CPU server node, and obviously comparing a whole rack of GPUs. So, you can do the math on cost, it costs more, but it's about 1,000 times faster because of being able to take advantage of really high performance GPU to GPU communication. So takeaway messages for everybody, HPC in general, ignoring all the AI stuff that's out there, ignoring all of quantum computing, HPC is changing from CPU to GPU centric. Obviously, that started about 10 or 12 years ago, and it's now almost all the systems in HPC are GPU based. And we're moving from the MPI plus X model where you took your CPU code and you threw in some OpenMP, and then you threw in some CUDA kernels. That just doesn't cut it anymore. We've got 4 or 8 GPUs per node, and you can't just start throwing 64 cores, 64 MPIs, and then try to have 64 MPI ranks scheduling across 8 GPUs with little tiny CUDA kernels that aren't decomposed big enough to saturate a GPU. So we need to move to much more GPU native thinking in how we design applications, refactor codes, redesign stuff, rewrite stuff, whatever it takes. Nickel's the natural evolution of MPI and to GPUs. And the thing that's interesting is nickel has gone through sort of an MPI3 transition, which I lived in MPI land, of course, many years ago, where we added one-sided and a lot of things changed in our usage models, and we had to rebuild how we did some of the applications. Nickel is supporting the RMA model, and that means that we're going to see a lot of different use cases for nickel. The old ones still work, obviously, and they're still critical in training, for example. But in reinforcement learning and inference, we're going to see more and more interesting communication patterns that are supported by nickel. The other thing, if you love Python, like a lot of people do, you can use NVSHMEM and nickel natively in Python now. This has been a big push for us. Obviously, you can get support in PyTorch, but you might just want to use nickel by itself in some Python application. I know, one of the Danish HPC codes is GPaw, and I've been talking to the GPaw developers about, you guys can just use nickel for Pi directly, and not have to worry about some of the overheads of MPI GPU support. So, the other part in the hardware side is that the GPU networking is really, really going crazy. You've now got over 1 terabyte a second of NVLink bandwidth in the latest generation NVIDIA systems with with load store connectivity to 72 GPUs, which unless you had an SGI Altix or an SGI Icebox or one of those old, CC NUMA machines of the past, you really don't know what that's like to be able to have the full memory space exposed with load store with that much. And obviously the compute that's in, 72 GPUs is quite a bit more than what was available in 1,000 Itaniums, like when I was using Altix. So lastly, to get back to our numbers where we started the whole talk with, GPUs can do millions or billions of operations in 1 microsecond. And therefore, overlapping these things using communication efficiently is really, really important. You do not want that GPU parked on a wait operation while the network goes off and moves things around on the CPU side. You want to have the GPU pipelining communication through the CPU or sending it directly off from the GPU and then fusing those kernels. There's no reason why you have to do math and then stop and then do a new kernel to move data and go back and forth. You can actually push these things together. And we're seeing a lot of these sort of mega kernel optimizations appearing in AI because those folks are really, really motivated to have lots of resources. But we'd really like to see these things happen as well in the HPC space because, everybody's paying a lot of money for systems. Everybody's got finite resources. We want to be able to use all these systems efficiently. So actually that's the end. So I'd be happy to take questions for as much time as people want to ask them. All right. I got to read the chat now. Just a second. There's a bunch of questions.
Your mic is off, Claudia. You should turn on your mic.
Finding bottlenecks.
So
okay.
sorry. So sorry.
Yeah. So Ricardo, good question. So there's a couple features for debugging. So this is a big focus area for us right now. So one thing you should be familiar with is Nsight systems. There's Nsight compute, which is really for kernels. And then there's Nsight systems, which is more about the whole system and data movement. There have been some improvements in that. So you definitely want to make sure you have the latest version and read the docs, for how it works with Nickel. Actually, I believe Marcus Herniak and Jerry Krause have a tutorial on MPI and Nickel that's on YouTube, and it's been shown at GTC. And I know it's at GPU mode because it was a week before I did mine. I believe they actually show that profiling activity for MPI and Nickel and probably NVSHMEM. So please check it out. The other one you can check out, there's something called the Nickel profiling interface, and there's Nickel Inspector. Both of those things will be documented on our website. Those allow you to capture different performance properties. I'm in the process of working together with the tools team on some debugging and profiling activities that hopefully will come out later this year.
The next one is from Remy, right?
Yeah, well, that one's similar. It's again profiling and diagnostics. The other thing I know you can, and I'm sorry, I'm bad with full names, but Didum has a lot of stuff on GPU comms that she's doing, and you can look at her papers and her talks. I don't know what her software releases look like, but she's talked about how to profile some of this stuff. So Joseph, is it possible to design a PGAS system that unifies them? Well, so from a runtime perspective, I like to have one runtime, so I'll say you could do it with one or the other. You could do it with both, but I would say we'd really like to get, if you build a system, I think you could build a system off of one or the other. Nickel doesn't have GET yet, the last time I checked, and it doesn't have all the atomics, so it won't be there right now. But can you build a PGAS compiler? Yes, I don't like compilers, and I don't know how they work, so I can't really tell you how to do it. But if you want to build a higher level abstraction, yes, that would be beautiful. I've worked on, NWChem and global arrays, and global arrays is basically a matrix array-oriented system on top of one-sided communication, and you could absolutely build, GPU global arrays on top of NVSHMEM. You could build it up top of nickel, but there'd be some caveats right now that will go away in the future. And actually, you can send me an email if you want to talk through that. I think it'd be lovely to see it. Right now, we're focused on enabling the AI frameworks, which have their own sort of layering systems in them that don't look like PGAS. But if you want to build a PGAS runtime for GPUs, I'd be happy to give you some pointers. Okay, that's a survey. Chapel and NVSHMEM. Okay, that's a great question. So Brad Chamberlain's a friend of mine, and I think Chapel's pretty cool. I haven't used it much lately. They could absolutely do GPU communication support, and for all I know, they could use NVSHMEM. I think they're still based on GasNet, and GasNet EX may have GPU support, in which case it may be. Oh shoot. Sorry. I hope I didn't lose too much there. Anyways, I hope that it may be the Chapel may be a fine situation, but yeah, I think you should talk to Brad and ask him what's going on. Any other questions?
Yes, I have a final question, and this is more on my AI parts, which is basically, well, AI workloads mostly focus on all-reduced communication, so all of the patterns are all-reduced. But do you know if there are other nickel communication patterns that can actually become more important and actually improve this synchronization and the synchronization? And even we all know that sometimes, and due to wearing and stuff like that, GPUs may stall a bit. And even though they're homogeneous, several GPUs, some of them can be actually slower than the others. So do you know that if there are any other communication patterns that we can actually use to improve this?
Well, yeah. So, there's a couple things. So that a lot of tensor math operations in training and inference are splitting up the all reduce into an all gather, reduce, scatter, like separately. That's and writing fused kernels that do those. I don't look at all the details, but I know that exists. In terms of what the new patterns are, a lot of them look like all to all. So there's expert parallelism, which is sort of this sparse all to all V pattern as I described here. The other one is sort of the all to all V that happens when you reshard, like you redistribute an array. You have one it's basically tensor transpose. I think you take one layout of your model and you redistribute it across GPUs. The other one that shows up is sort of a weight transfer. So when you have reinforcement learning, you have training and inference happening in the same place. So you're going to train and you're going to update your weights, and then you're going to have to make your weights move to where your inference happens, and then this happens in a loop. And that looks more, it can look, I think, sort of like either all to all, or there's a broadcast angle or an all gather to it. And it obviously depends greatly on how somebody sets up the system, how they design their framework, how that works. But I think, one of the things that we're seeing is to move away from sort of global all reduce. Obviously, that's still relevant to training, but with a lot of the mixture of expert stuff, you now don't do one big all reduce. You do these local MLP contributions and then do the expert combined sum, and that does break things up quite a bit. As for noted the load balancing scenario. Yeah, that one is in some cases is just plain hard. You have to really come up with new math to make things you can remove all the synchronization from the network, but if the math is still both synchronous and one GPU runs slower than another, it eventually that'll show up somewhere. And so I think there's still just a lot of research to be done. I saw Francesco had a question about MLIR. And I know that my coworkers have been working on that. I don't know I don't know what it looks like. I don't know what is shipped. But you know, there's Triton and Triton Distributed, and I think Triton Distributed from ByteDance has some system like this that you should look at. But yeah, the MLIR support for GPU comms is increasingly important. I just unfortunately haven't kept up with what's available right now there, but there are things happening.
Okay, thank you so much, Jeff, for all of for the presentation and even to answer all of these questions. Actually, I think it was a really interesting webinar and very different from what we're used to, because it focused really on nickel and this stuff. Yeah, I think there's one more question. No? Okay. Someone raised the hand, but then just went out. So let me just finish this up and wrap everything. But once again, Jeff, thank you so much. It was really, really been a pleasure to actually have you here, and for all the answers and even the work that you have been doing. So thank you all the participation as well, the participants, and thank you for all of your questions. Actually, I will leave you with the webinar series on profiling. Eventually, you can register now, and you have 5 webinars scheduled. So even for the questions that Ricardo raised, maybe you can look at it. And even I think it was Jaime, you can also look at it, because we have 5 webinars that actually look into several problems and how to profile several problems that may arise in HPC environments. So thank you so much. You can already register for this series of 5 webinars, and please stay tuned to our communication channels for more information. And please, thank you once again. Thank you, Jeff. So I think it's
Thanks,
done.
everybody.
Thank you a lot. Bye-bye.
Bye-bye.